This is video 17C for the Year 9 Mathematics course. In this video, we're going to cover the theory behind gradient, under the topic of coordinate geometry. Specifically, we're going to explore the definition of a gradient, positive and negative gradients, the gradient formula, vertical and horizontal lines, finding a second point using gradients, and then we're going to cover some example questions. Alright, so along this discussion on coordinate geometry, we're now going to move into probably one of the most important aspects of any line of study regarding coordinate geometry, and of course I'm talking about the gradient, or in other words the slope, of straight lines. Now, cast your mind back to a couple videos ago when we were talking about calculating the distance between 2 points. So in order to do that, what we did was, let's say we had this point here and this point here. Then in order to calculate the distance between these 2 points, we would first of all draw a line segment connecting these 2 points, and we would say that this line segment has a length of d units. We would then calculate this length d, as this represents the distance between the 2 points. So now that we're moving into this discussion of gradient, what we're now going to be ultimately concerned about is the steepness of this straight line. And when we refer to the steepness of a line segment, we use the terminology gradient. Also sometimes referred to as the slope of the line. Now, coming off of this definition here, where we're now going to be considering the overall steepness of the line segment, the first thing that we're going to do is consider what it means to have a big gradient and then a small gradient. So if I were to draw out this line segment here and this line segment here, can you maybe take a wild guess as to which one's going to have the greater gradient or slope? It's going to be this first one here. And this is because the line segment is physically steeper than this one here. Whereas this line segment here is going to have a smaller gradient because it is not as steep as the other line segment. However, of course, what we know about straight line segments is that they do not strictly have to move in an upwards direction as we move to the right. We have two different situations that can happen. We can either move the straight line upwards as we move to the right, or the line can move downwards as we move to the right. In this first situation here, the gradient would be defined as a positive number. Whereas this line segment here would have a gradient which is defined by a negative number. So that's our first really big learning point when it comes to gradients. A positive gradient means that the line moves up as we move to the right, whereas a negative gradient means that the line moves down as we move to the right. Now the next question is, how do we go about actually calculating the numerical gradient of different straight lines? Well, if I were to consider this example over here, where we've got these 2 points, and then we connect these points using a straight line segment, so just like that there, then the way that we actually define the gradient is using a quotient where we have the rise over the run. Now, what do we mean by rise and run? The rise is effectively a measure of how much we go up or down by, whereas the run is how much we move horizontally by. Or in other words, we have the vertical movement over the horizontal movement. So if we're going to consider this generic line segment over here, the run would be this horizontal movement here between the 2 points. And then the rise would be this vertical movement here between the 2 points. So we can see that we've already got a lot of similarities between how we consider the distance between 2 points and then the gradient. Because as you may recall, when we were calculating the distance between 2 points, we considered this distance here and this distance here. The way that we use the two distances, however, very, very different. Now, what we sometimes refer to the rise over run as being is the y jump over the x jump. And again, this is just by using very similar terminology to what we did when we considered the distances between 2 points. It's effectively a measure of how much we move up or down by, divided by how much we move horizontally by. And so, of course, what we're going to look at now is how we generalize finding the gradient between two arbitrary points. So, what I'm going to do here is I'm going to classify two arbitrary points as x1, y1 and x2, y2. I'm now going to sketch up a quick generic Cartesian plane. So we've got that one there. I'm just going to say that this point here has coordinates of x1, y1. And then this point over here is our second point at x2, y2. Now, we of course know that the gradient connecting these 2 points, or in other words, the slope, is given by rise over run, or in other words, the y jump, divided by the x jump. Now, first things first, the x jump is effectively a measure of how much horizontal distance there is between these 2 points. So it's going to be this line segment here. And then the y jump is a measure of the vertical movement between these 2 points, or in other words, this vertical line segment there. Now, let's see if we can express the x jump and the y jump in terms of x1, y1, x2, and y2. So let's start off with the y jump. So we can see that this point here is aligned with y1 and that this point here is aligned with y2, which therefore means that this distance here is going to be given by the difference in these two y coordinates. So in other words, this rise is going to be given by y2 minus y1. And then furthermore, we can see that this point here is aligned with x1, and that this point here is aligned with x2. And so therefore, the horizontal jump, or in other words, the x jump, is going to be given by the difference in these two x coordinates here, or in other words, x2 minus x1. And so therefore, we can conclude that the gradient, which is given by rise over run, is equal to y2 minus y1 divided by x2 minus x1. Or in other words, the difference in the y coordinates divided by the difference in the x coordinates. Now, a few very, very important things about this particular equation here. You need to make sure that these two coordinate points here are a pair, and that these two coordinate points here are also a pair. As in, these two values here should combine to make the coordinates of one point, and then these two values here should combine to make the coordinates of the other point. As soon as you start getting these values mixed around, you are going to end up with a very, very incorrect answer. So similar to what we mentioned in our previous two videos, one of the best things that you can do whenever attempting questions like this is to first of all classify the 2 points that you have as point 1 and point 2, and then actually label out the values of x1, y1, x2, and y2. And then final thing I'm just going to quickly make mention of about this type of calculation here is that 99.9% of the time, if you get an answer which is a non-integer, always leave your answer as a fraction. We tend not to work with decimals when we're calculating gradients just because they do tend to make things a little bit harder. So always leave your final answer, if it's a non-integer value, as a fraction in simplest form. Now, when I talked about gradients earlier, I did tell a bit of a lie, because what I said earlier was that there were two different situations that we could consider when we're talking about gradients, either positive gradients or negative gradients. That is a bit of a lie, because of course when we are talking about numbers, we know that positive numbers and negative numbers aren't the only numbers that we have to consider. So let's talk about these other cases now. So what I'm going to do here is I'm going to present two somewhat more interesting situations that we could deal with. The first situation is what happens when our line segment is perfectly horizontal. And the second situation is what happens when the line segment is perfectly vertical. So for a horizontal line, what this effectively means is that we're going to have 2 points to connect for this line segment but are aligned vertically. Whereas for the vertical line, we're going to consider 2 points that will connect using a line segment that are aligned horizontally. Because now if we connect these two pairs of points using straight line segments, we get the following. Now, if we just give these points some arbitrary coordinate values, for this first situation here, let's say that this x-coordinate is x1 and then the second x-coordinate is x2. But then because these 2 points are aligned vertically, they can both have the same y-coordinate of y1. Then for the second situation, we can say that this y-coordinate is y1, this y-coordinate is y2. However, because both the points are aligned horizontally, they can both have the same x-coordinate of x1. And so therefore, in the situation of the horizontal line, the 2 points that we're going to be considering are x1, y1, which is this point here, and then x2, y1, which is this point here. For the vertical line, we've got x1, y1, which is this point here, and then we have x1, y2, which is this point here. And so therefore, in the first situation for the horizontal line, if we wanted to calculate the gradient of this straight line segment, we get the rise over the run. So in other words, we're going to get the difference in the y coordinates. So we'll do y1 minus y1. And then we'll divide this by the run, which will be x2 minus x1. Now, in this particular case here, we of course know that y1 take y1 will be equal to 0. So we have 0 over x2 minus x1, which is equal to 0. Now for the vertical line segment, if we wanted to calculate the gradient here, we will first of all get the rise, which will be y2 minus y1. Then we will divide this by the run. The run in this case will be the difference in the x-coordinates, which will be x1 minus x1. And then in this particular case, y2 take y1 can just stay as it is, but then of course we know that x1 take x1 is equal to 0. And what do we know happens in maths when we divide by 0? We get what is called an undefined result. Or if you prefer to think about this in a slightly different way, this effectively means that our answer is infinite. So, let's now carefully examine what both of these situations mean. For any horizontal line, the gradient is equal to 0. And when you think about it, this kind of makes a whole lot of sense, because effectively the gradient is a measure of how steep the line is. However, we of course know that a horizontal line has no steepness, so therefore a gradient of 0 makes absolutely perfect sense. But then moving on to the vertical line, we can see here that a vertical line has an undefined, or in other words, an infinite gradient. And that is because in this particular case here, we can see that a vertical line effectively has an infinite steepness because it just goes straight up. So these are our two special cases that we have to consider as well. Horizontal lines have a gradient of 0, and vertical lines have an undefined, or in other words, an infinite gradient. Now, before we move into some example questions, there is one final point here that we do need to touch on, which is going to be very, very important for any situation in which we're working with points and gradients. And so what we're going to be looking into now is the situation in which we are provided one point on a line segment, we are provided with the gradient of that line segment, and we then want to find out what a secondary point along that line segment could be. And so what we're actually going to do here is use the original definition for gradient, which we know is rise over run. Or in a bit more of a casual sense, the gradient effectively tells us how much the line moves up or down by as we move to the right by 1 unit. So what I mean by this is, let's say we had a gradient which was equal to 4. Then what this here therefore tells us is that as we move to the right by 1 unit, we move upwards by 4 units. Or if we had a gradient which was equal to -2, then this here tells us that as we move to the right by 1, we move downwards by 2 units. And so therefore, we can use this idea here in order to find a secondary point if we already know one point along the line segment itself. So what I mean by that is, let's say we were provided with this generic point here, which had coordinates of x1, y1. And we wanted to find a secondary point, which was somewhere over here. And we were told that the line segment has a gradient of some number, let's just call it a. Then what this here therefore means is that as we move to the right by 1 unit, then we're going to move upwards or downwards if it's a negative number by a units. We can then use these two coordinate values here alongside with these two movements to then find what the coordinates for the secondary point are. Now, this idea here is all well and good if we're working with integer values for our gradient. However, in certain situations, we may actually be working with fractional situations instead. So if we instead wanted to consider situations in which the gradient was a fraction, we'll say the following. So let's say in this scenario, the gradient was equal to a over b. So just a generic fraction of a over b. Well, we know that the gradient is equivalent to the rise over the run. So again, let's say if I consider this provided point here, which has coordinates of x1 and y1, and I wanted to find this secondary point over here. And as we just said here, we know that the gradient of the straight line segment connecting these 2 points is given by a over b. Then by using this idea over here, we can say that the rise between these 2 points is given by a and the run is given by b. So in other words, to go from this point to this point, we're going to be moving horizontally by b units, and then we'll move vertically by a units. And so then you combine these two coordinate values with the run and then with the rise to find out what the coordinates of this secondary point are. But again, use this when your gradient is in fractional form. If it's just as an integer, then we can use this idea that we just displayed here. But again, it's very much dependent on whether your gradient is an integer or as a fraction. So just be very, very careful with that. But the overlaying idea is still very, very similar. Alrighty. With that now being said, let us have a look at a few example questions surrounding gradient. Alright, so the first example that we're going to consider is to find the gradient connecting these 2 points. So we've got 2, 5 and 6, 1. Alright, first thing I'll do here is classify this point as point 1 and then this point as point 2. So therefore the 2 is x1, the 5 is y1, the 6 is x2, and then the 1 is y2. And so therefore, the gradient of the straight line segment connecting these 2 points is given by y2 minus y1 divided by x2 minus x1. This here simplifies to negative 4 over 4, which is equal to negative 1. So therefore, the gradient of the straight line segment connecting 2, 5 and 6, 1 is equal to negative 1. Then the second example that we're going to consider is the following. Let's say we started with the point 2, 4, and this point is on a line segment that has gradient equal to negative 4 over 5. And we now want to find out a secondary point along this straight line segment. Alrighty, let's start off with this gradient here, because we of course know that gradient is equivalent to rise over run, which therefore means that on this straight line segment, we move vertically by negative 4 units, and we move horizontally by 5 units. So if I were to just draw up a quick representation of this situation, so we've got this provided point here at 2, 4, and to find a secondary point, we're going to say that we'll move horizontally by 5 units. So we're going to move this way by 5 units, but then we're going to move vertically by negative 4 units. So we're going to move downwards by 4 units. And then this here is the point that we want to try and find the coordinates for. Now we know that the x coordinate is going to be 2 plus 5, which is of course 7. And then the y coordinate will be 4 minus 4, because we're moving downwards, or in other words, 0. So a secondary point along this straight line segment will be 7, 0. Alrighty, let's summarize what we've learnt today. So in this video, we discussed the gradient or slope of straight lines, which act as a means to measure how steep the line is. A line with a positive gradient moves up to the right, whereas a line with a negative gradient moves down to the right. The gradient is also defined by the quotient rise over run. That is, how much the line moves up or down by, divided by how much the line moves across by. Hence, the gradient of a line connecting the points with coordinates x1, y1 and x2, y2 is given by y2 take y1 all over x2 take x1. To make this calculation easier, we can first classify our points as point 1 and point 2, and hence identify the values of x1, y1, x2 and y2 respectively, and carefully substitute them into the gradient formula. Horizontal lines have a 0 gradient, since there is no slope. Vertical lines have an undefined gradient, since they have an infinite slope. We then explored how we can use a provided point and the gradient to find another point on the line. We can do this by considering the fact that the gradient is equal to rise over run. When provided a point with coordinates AB and gradient m over n, then a second point on the line will have coordinates a plus n, b plus m. Finally, we applied these ideas to some example questions. And that's it for now. See you in the next video.